Hi there, welcome back. Let's continue our discussion about dependence measures. In this class, we will see some possible alternatives to the correlation we have considered last time, which is, in the statistical world, more precisely known as Pearson's correlation. As we have seen, in a linear world and under normality, which is somehow like assuming a linear world, correlation is a wonderful measure of dependence, which is able to capture perfectly the linear dependence between two or more random variables. Unfortunately, the world is not linear and not even Gaussian. When we consider losses, for example, we know that the distribution of losses of the average bank is skewed on the right with a fat tail on the right, meaning that larger losses are much more frequent than what we could expect under a normal distribution. And consider very simple securities and financial products like options. Okay, these are nonlinear products. Typically, the relationship between the underlying asset, the price of the underlying asset, and the value of the option is not linear. So what happens when we lose linearity and when we lose normality, which is the nice framework in which correlation is the best measure we can think of? Yeah, the problem is that correlation is no longer the best measure. We have to find something else. And if we consider fat tails, I want you to think about one thing. We know that it's quite common in finance to find fat tail distributions that are so fat in the tails that the variance, the second moment, is not finite. Now, I'm speaking about the theoretical distribution. Obviously, in the sample, you will always be able to compute a finite value for the variance. The problem is that that value is totally meaningless. So, if the theoretical variance is not finite, what happens? Okay, correlation is not defined. Why? Because look at the ratio that defines correlation. We have the product of the standard deviations that are the square roots of the variances. But if the variances are infinity, then what about the square root? Correlation cannot be defined. A possible solution is represented by rank correlations that are a group of measures of dependence that depend only on the joint behavior of two or more random variables and not on the marginals. In order to compute rank correlations, we must be able to transform the data we observe into ranked observation. That is to say, we must be able to reorder the data in terms of magnitude. Now consider 2 points in R2, xy and x tilde y tilde. We say that these 2 points are concordant if their coordinates move in the same direction. They are discordant if, on the contrary, they move in different directions. A first measure in the rank correlation class is represented by Kendall-Stau. Kendall-Stau starts from the observation that if we have two random variables x and y tends to increase with x, tends to move in the same direction of x, then the probability of observing concordant couples of observation will be higher than observing discordant couples of observations. As Pearson's correlation, Kendall-Stau takes values in the interval -1, 1, but the interpretation is different. First of all, Kendall-Stau is not restricted to the case of linearity. And a Kendall-Stau of 1 tells us that the two random variables x and y have a perfect agreement for what concerns rankings, and there is a strong positive dependence between the two. In the case of a Kendall-Stau equal to -1, we are exactly in the opposite case, and when Kendall-Stau is equal to 0, we are not considering uncorrelated random variables, but independent random variables. As for Pearson's correlation, we can also define Kendall-Stau for multivariate vectors. In that case, we will obtain a sort of correlation matrix on which on the main diagonal we have 1s, because the Kendall-Tau of x with x is obviously 1, and on all the other positions of these correlation matrix we will have Kendall-Staus. From an empirical point of view, Kendall-Stau can be computed using the formula you see on your screen. That is to say, the number of concordant couples minus the number of discordant couples over the total number of couples we can define in our sample. Another rank correlation measure, another famous one, is the Spearman's rho or Spearman's correlation, which is nothing more than the basic Pearson's correlation that we compute not on the rho observation but on the ranked ones. A very convenient representation of Spearman's rho, which is probably a little bit more intuitive, is to see it as the standard correlation between the probability transformed random variables. So we do not consider x and y, but using copulas, we use their copular representation, so f of x and g of y. If we assume some specific functional form for the copular relationship between x and y, we can compute Spearman's correlation analytically. Here below you see the representation when we assume a Gaussian copula between x and y. Now, if you plug in any value of rho, the Pearson's correlation, you will see that the value you get for Spearman's correlation here below, it's quite close. Why? Because since we are assuming a Gaussian copula, we are essentially imposing a linear dependence between x and y. So look at the three pictures in front of you. In the first one, the three measures, Pearson's correlation, Kendall-Stau, and Spearman's rho, essentially agree on the fact that between x and y there might be some positive dependence, possibly linear, but not extremely strong. In the second example, we have that most of our observations are condensed in a cloud where we can really see some strong linear dependence. But on the right, we also have a smaller cloud of points. This fact somehow tricks Pearson's correlation, which is now 0.65. On the contrary, Kendall-Stau and Spearman's rho seems to be immune to this situation and still tell us that there is a strong dependence between x and y. Finally, in the third example, we have a nonlinear relationship between x and y, and both Kendall-Stau and Spearman's rho give a value of 1 because you see the points are exactly following a specific pattern that we can really observe. For what concerns Pearson's correlation, the value is high, 0.75, but remember that in this specific case, this is not really meaningful because the relationship between x and y is not linear. The linearity we observe using Pearson's correlation could lead us to very dangerous consideration when dealing with the left and the right tail in the data. When dealing with tails, we can introduce the so-called coefficient of tail dependence. This is a rather important coefficient because we really might be interested in knowing what is the degree of dependence between x and y when we observe extreme events. Because when we are in the bulk of the distribution, actually dependence can be important, but if we consider losses, we are dealing with losses we can manage. But when we are dealing with very extreme losses, there, knowing if there is a strong dependence between the two random variables becomes crucial. The tail dependence coefficient is defined in terms of tail conditional probabilities. Set a p very high, say 99.9%. The tail coefficient tells us what is the probability that y will be above its 99.9% quantile, given that X is above its 99.9% quantile. Consider we have a portfolio with just two counterparties. With X and Y, we represent their losses. Now, the coefficient of tail dependence, if our quantile is the 99.9% var, tells us what is the probability to observe a loss for Y larger than the 99.9% var, given that we have observed a loss larger than the 99.9% var for X. This is a very important information when you are dealing, for example, with portfolio losses during a crisis. The coefficient of the dependence ranges between 0 and 1. 0 tells us that there is no tail dependence. 1 is perfect tail dependence, is comonotonicity in the risk. Assume that our X and Y are linked by a Gumbel copula, which is a special type of Archimedean copula with positive tail dependence. Now, in this specific case, the tail coefficient can be computed explicitly, and you see the value on your screen. Now, look at the graph. These data are generated by a Gumbel copula. If we compute the correlation between X and Y, we find a value of 0.75, which is a value that indicates a quite strong linear dependence between the two random variables. And this is actually what we can see on the screen. But if you look at the right tail, you see that there the dependence between X and Y becomes stronger. And this is captured by the tail coefficient. If we ignore this information and we just consider what happens in the bulk of the distribution, and we just rely on our 0.75, we could really seriously underestimate the tail of the distribution, of the joint distribution. We could really underestimate the strong dependence between X and Y when we deal with extreme events. So since in risk management and credit risk management we are quite interested in tail events, it's always important to remember the existence of these type of measures. To enter into the details of the tail coefficient, we would need extreme value statistics, which is something I cannot assume, so I will skip it. Naturally, if you are interested, you can write me anytime, also after this course. You have my email address, so I'm very happy to answer your questions. And actually, extreme value theory, it's my field of research, so I really like it. Now, the point is that we can continue our discussion about dependence measure. There are many different dependence measures, like, for example, nonlinear correlation, even if this is a definition I don't like, and other different rank correlations. My message for you is be free to use correlation, be free to assume linearity, but always remember that you are imposing a structure on the data. And if you know that your data are not linear, then look for an alternative. Don't rely on Pearson's correlation. Most of the models we have seen together can be transformed using the new measures of dependence. So think about that. That was it. Thank you for your attention. Goodbye.